Peter Orbans is kindly chairing the next session.
Hello. Our next speaker is Francois Caron. Francois is at Oxford, Stats Department. Most of his work is based on parametrics, and he's done a lot of very nice stuff based on parametrics. Today he's going to speak about generating graphs from exchangeable random measures.
Thank you. Thank you very much for the invitation. So this is joint work. So for most of it with Emily Fox at University of Washington, and for the latest developments with my student Adrien Todessini at INRIA. So I will be interested here in simple graphs. So where you've got a set of nodes or vertices and undirected connections between them. So for example, the social network, protein-protein interaction, internet, etc. And I will be so interested in developing a statistical network model that can so capture some of the features of real-world network, and in particular, so I will be interested in the property of sparsity. So what is so the definition I will take of sparsity? So we call also dense graph is a graph where the number of edges scales quadratically with the number of nodes, and so we call sparse a graph that is not dense, so where the number of edges scales subquadratically. So as mentioned by Peter in his previous talk, so it's believed that a lot of the real-world networks are actually sparse. I'm interested also in developing some model that can have some sort of heavy tail degree distribution, and where we can capture some sort of latent structure. And then I want to have a set of parameters and make inference on those parameters, and I would like those algorithms to be relatively scalable with the size of the network. So classical approach to network modeling or Bayesian network modeling is to represent, so if I'm interested in an undirected graph, so it's to represent the graph as a discrete structure, so the adjacency matrix, xij, which is a binary matrix, where xij is equal to 1 if there's a link between node I and node j. And so if we want to have some sort of symmetry, also as mentioned by Peter, a classical assumption is to assume that the way that you order the nodes is of no importance, and so it translates into the notion of joint exchangeability. So this binary matrix xij is invariant over any joint permutation of the rows and the column. Okay, and this for any permutation pi of n. So if you make this assumption, so you've got some representation theorems, so due to Aldous and Hoover, so for exchangeable binary matrices, and so as nicely shown in this review by Peter and Dan Roy, so many Bayesian models of networks so fit into this framework, so Bayesian version of stochastic block model, etc. But as a corollary of the Aldous-Hoover theorem, so if you use this exchangeable binary matrix to represent your network, then you end up with graphs that are so either empty or dense. And so if you believe that your network is actually sparse, so then you obtain a model that is misspecified in the sense that it necessarily leads to a dense graph. So what do people do to handle sparse graphs? So you cannot have infinite exchangeability and sparsity. So one way to address this is to just so you need to give up infinite exchangeability. So you can have just non-exchangeable generative models. For example, preferential attachment is one of them. So what a lot of people are doing as well is to consider sequence of finitely exchangeable models. So you've got for a given sample size n, so you've got a model xij of n, for ij is equal to 1 from n, where the model for a given n is finitely exchangeable. So one example is this Chong-Liu model, for example, or a lot of people are looking at sparsification of the graphon. So where for a given n, so xij of n is obtained by some rescaling by a parameter rho n, where rho n goes to 0 as n tends to infinity. So there's very nice theory on this. So from the point of using this as a probabilistic model of the network, so the issue is that you've got a collection of models that are not consistent between each other. So if you take the model with n plus 1 and you marginalize it, you don't obtain the model with a sample size n. Okay, so we take a different approach. So we won't use a binary matrix. So what we are going to do, so instead, so we are going to represent the graph as a point process on the plane. And so what I will show, so there's similarly to binary matrices, so there's also some representation theorem, so due to Kallenberg, for jointly exchangeable point processes on the plane. And within this framework, okay, so I show that we can use some sort of a construction which is based on vectors of completely random measures. And we'll use some properties of the model. So we show that this model is so exchangeable in the sense of exchangeability for point processes, that we can have sparsity. So the number of edges grows subquadratically with the number of nodes, power law degree distribution, have some sort of structure as well, so in terms of overlapping block structure. And so if we're interested in the statistical application, so we can characterize the posterior distribution under this model and derive so Monte Carlo algorithm to estimate the parameters of this model. So I now describe the representation of the graph. So the way I will represent an undirected graph, so I will represent it as a point process on the plane. So I will assume that each node has some sort of location in R plus, which is noted here theta I. Okay, so you can think about theta I as a latent location of the node or time arrival of the node. And I will assume that there's a connection between node I and node j if there's a point at location zij. So here, if this is the location theta I, theta j, so there will be a point at location theta I, theta j if there's a connection between node I and j. Okay, so this represents a self-connection between this node, etc. So, and so here I've got 4 nodes with at least one connection and 5 edges. So this is the, so I will work now with this object, okay, so with this point process that will represent my network. And so what's the notion of exchangeability for point processes? So I've got my point process on the plane, and if I look at any edge and any regular grid on the plane, so I take a regular grid on the plane and I count the number of points within each of those squares. So it gives me an infinite dimensional matrix, and I want this matrix to be exchangeable with respect to any joint permutation of the rows and the column. Okay, so exactly the same definition as I've said, and so this has to hold for any value of edge. So it turns out, so if you make this assumption of a joint exchangeability for this point process, you've got a representation theorem, so some sort of a coding of the point process in terms of transformation of unit rate Poisson processes. And the construction I will take fits in this framework. Okay, so so this is what I want to have, and so now I will explain a particular generative process for this point process, and describe the properties of this model. So as I've said, I assume that the nodes are embedded at some location theta I, can be interpreted as a time arrival, and now we will add parameters. So we'll assume that each node has a set of positive attributes wi1, wip. So if p is equal to 1, so you can interpret this parameter as a sociability parameter. So the larger this parameter, the more likely the individual is to connect with other nodes. Okay, if p is greater than 1, you can interpret those parameters as the level of membership of an individual to a particular community. So one individual may have different interests that are reflected into those attributes. And so the key points, so now I want to define some model on the location theta I and those positive attributes. And I will model those by the use of a vector of completely random measure on R+. So I will consider random measure wk, which are the sum from I equal 1 to infinity of wik delta theta I. Okay, so I've represented here a vector of completely random measure. So at location theta I, I've got a vector of attribute wi1, wi2, wi3. And this vector of completely random measure is basically characterized by a mean measure nu that I will assume will decompose into two parts. So one part that will tune those features, so which is rho here. So rho is a Levy measure, and the part of the location, and here it's just the Lebesgue measure. So the important part is this Levy measure rho here that will tune the distribution on those positive parameters. So I will distinguish two important parts. So if you assume that the integral of rho is equal to infinity, so this means that if you look at any interval 0t, you will have an infinite number of jumps in 0t. So you can interpret this as if you look at a finite amount of time, you've got an infinite number of individuals, each one with its own sociability. And if this is bounded, then in any interval, you will have almost surely a finite number of jumps in 0t. So those two distinctions are important because they will translate into the property of the network. And so, okay, how do I construct the network based on this? So it's very simple. So for any couple, so I, J, the probability that there's a connection between I and J, so we use a link function that is relatively standard in network modeling. So if I is different from J, so it's 1 minus exponential minus 2 sum from k equal 1 to p of wik wjk. And so this is represented here. So there will be a point at this location theta I, theta j with this probability, where here you got the weights, the weights of in the different features. So why do we have this link function? Because then there's some sort of a latent Poisson construction of the model. Okay, so in the construction, so if two individuals have shared interest in the same feature, they will be more likely to connect than individuals that are different types of interest. Okay, so now I will so show you some simulation from the model. So as I will start from the so the way my network will grow. So I start from the upper left corner, okay, and I look at a box alpha that increases, and so this will increase the size of my network. So on the left, so you will have the point process starting from the upper left corner, and on the right, so the associated network. Okay, so you got here the point process in blue and the completely random measure with the jumps corresponding to the sociability of the nodes. And on the right, so this is the associated network where the size of a node is proportional to its degree. And so what you see, so where you've got a large jump correspond to a high degree node. So here we got. Okay. Yeah.
I didn't understand what role K is playing. K is the dimension of the.
So
you get the same picture with K is 1.
you mean P? You mean P?
P. Yeah.
Oh yeah. So okay. So yeah. Sorry, I should have
Wouldn't the
mentioned
picture
it.
be the same with
So-
K is 1?
So in this figure there is P equal 1 here. So there's just one feature. So here you can interpret the jump in the red jump as just the sociability. So I assume that there's just one parameter that tunes the sociability here. So there.
Well, so far it hasn't played any role in your.
P, no. Yeah. I'm going to. Okay. So I'm interested now in looking at the sparsity of the model. So as I've said, so the size of my network, so I consider a box here of 0 alpha squared, and I'm increasing the size of the network by increasing the size of this box, okay? And I'm counting, so the number of n alpha e is the number of edges, and n alpha so is the number of nodes, okay? So correspond to the number of nodes actually with at least one connection. And I'm interested, so I've got here an integer value stochastic process, so n alpha, and a stochastic process n alpha e, and I'm interested in the asymptotic behavior of the number of edges compared to the number of nodes. And so what we can show, so under some assumption that the network won't be trivially empty and under some moment condition. So if we look at the behavior of the number of edges compared to the number of nodes, so you can directly relate the asymptotic behavior to the properties of the completely random measure. And so in particular, if the completely random measure is finite activity, then you end up with a network which is dense. And if the vector of completely random measure is infinite activity, then you end up with a model which is sparse. And you can actually even characterize more finely so the behavior in the sparse regime as well.
What does it mean to have finite activity?
Oh, okay, yeah. So finite activity. So it means if you look at an interval 0t, you've got almost surely a finite number of jumps. Okay, so here, so I'm looking at if you stop at alpha, and you look here the number of jumps over 0 alpha. So if it's finite activity, you will have a finite number of jumps. If it's infinite activity, you have an infinite number of jumps. Okay, so in a sense, you've got an infinite population of individuals, each one with its own sociability parameter, but only a finite number of them actually have at least one connection. The infinite remaining ones have no connection at all. Okay, so now just to give some illustration. So if p is equal to 1, so you can interpret this parameter as a sociability parameter, and I will look in particular to this Levy measure, so which is so Levy measure of generalized gamma process. So we've got two parameters, so the parameter alpha and the parameter tau. And in particular, so I'm interested in this parameter sigma here, which will tune the sparsity of the network. So what is nice with this model, so you've got both the sparse regime and the infinite activity property when sigma is greater or equal to 0, and when sigma is negative, then you have a finite activity process, and you are then in the dense regime. And so here are just some simulations for comparison. So this is the Erdos-Shreni random graph with 1,000 nodes and probability of connection 0.05. And here, so draws from the model so for different values of sigma. So sigma is equal to 0, sigma is equal to 0.5, sigma is equal to 0.8. And as the parameter sigma goes from 0 to 1, you obtain networks that are sparser and sparser, which might not be obvious in the picture. Okay, and so looking at the degree distribution also, you've got some power law-like behavior for the degree distribution. So if you look at those three red curves, for example, so it's the on the log plot. So you've got the empirical degree distribution for different values of sigma. Sigma is equal to 0.2, 0.5, 0.8, and the parameter sigma so directly relate to the slope and to the exponent of the degree distribution. Tau has some sort of interpretability as well because it will tune the exponential cutoff in the tails of the degree distribution, which is seen here for different values of tau. Okay, so it was for p equal to 1. So now if you want to have more structure in the model, so with some sort of latent communities, so you've got some multivariate here Levy measure. And so we need to find some sort of parametrization for this. So we've looked at using the framework defined by Griffin and Leisen on compound completely random measure. So where the Levy measure basically will be parameterized by one Levy measure rho 0 on R plus. So this base Levy measure will kind of tune the sparsity level of the network, and some score probability distribution that will tune the level of affiliation of the nodes to the different communities. And so it's possible to write this Levy measure under some hierarchical construction. And so here it's just, so for illustration, so it's a draw from the model, so where P is equal to 3, so you've got 3 different communities. The size of the node is proportional to the degree of that node, and the color of the node is proportional to the level of affiliation of each node to the 3 different features. Okay, so here it's nodes that are primarily with the red feature. Those ones have a mix of the red and the green. Those ones have a mix of those two, etc.
And what was D? D? In the previous slide?
There was a D.
You were on R. You were on RD.
Ah, okay. Yeah, good. So P.
Oh,
Oh no. What's the P? Yeah.
P.
Yeah. Sorry. Where's put it? Okay. So what do we want to do with this model? So it has interesting properties. So now what we do, so we observe a set of connections. So that right, Zij from ij is equal 1 to n alpha. So in my model, I had some node location theta I. Actually, those node connections are independent of the so those node locations are independent of the connection, and I won't try to infer them. They are not likely identifiable. So what I want to learn some set of hyperparameters. So in particular, this sparsity parameter sigma. And so what I want to know, I want to learn the parameters of the nodes for which I've observed at least one connection that I write. So W1k, Wn alpha k, which is the set of weights of the so for the feature k, those are the n alpha weights. And also, so as I've said, so there might be potentially an infinite number of jumps. So what I want to learn also is the W star k. So W star k is the sum of the parameters of all the nodes that have no connection. Okay, so under my model, I might have an infinite number of individual, and only a finite number of them connect. And what I want to learn is the sum of the sociability of the other nodes. And so what we do, so we can derive an MCMC sampler to do posterior inference under this model. Thank you. So yeah, I won't detail it. Just show some, some simulation. So here on some simulated data, so I simulate a graph from this model. So with this set of parameters. So alpha is equal to 1/2. So I am in the sparse regime. so I simulate from this model and I obtain a network with 14,000 nodes and 76,000 edges. And so what I do, so I run an MCMC sampler with 3 chains, 40,000 iterations. So just to say that so I've got 1 parameter per node. Okay, so I've got about 14,000 parameters, but the algorithm is relatively efficient. It takes only 10 minutes here on standard desktop. And so if we look at the estimation of the parameters, so parameter alpha, parameter sigma, so the sparsity parameter, parameter tau, and W star, so which is the sum of the sociability parameter for all the nodes. So we see that we can recover those parameters quite well. And if you look, so we do Bayesian inference, so we want to have credible intervals on the sociability parameters of the nodes. So on the left, I represented in green the sociability parameters of the nodes with highest degree. And in red, those are the 95% credible intervals. So what we see is that so we recover those credible intervals quite well. And the same for the nodes with lowest degree. So because the network is power law, so actually all of those nodes have degree 1, and so here this is the log sociability on the log space. So we can recover as well the credible intervals relatively correctly. Okay, so yeah, I won't say again. So just some illustration now with p greater than 1. So we managed to have the algorithm work. So when p is equal to 1, the algorithm scales very well to large networks. When p is greater than 1, we still need to work a bit on it. So it works for a network to 2,000 nodes, but yeah, we hope that we will manage to handle larger networks. So here we look at the undirected network of US airports, so 1,800 nodes, 44,000 edges, and we're using here p equal 4 latent features.
How did you estimate that?
So yeah, how did
you choose 4 latents?
Oh, 4, yeah, so it's I think that's a very interesting question, how to set p. Yeah. And so yeah, so we run MCMC sampler on this network, and so we learn those 4 parameters for each node. So what I've represented on the left, this is the so the adjacency matrix reordered by so we reordered each node by the feature that has the highest value. Okay, and so you can clearly so those nodes have feature 1 that has the highest value, feature 2, 3, and 4. So we can see obviously some sort of block structure in it. And if we and on the right, so I've represented for different nodes. So the value of the weights, the relative value of the weights of the 4 different features, and so it's quite easy to interpret those features. And actually, so this network has already been analyzed with a standard stochastic block model, and so you can interpret those features. So one can interpret it just as large hub, so large airport that can be anywhere in the US. One feature is clearly airport on the east. The other one is west, and the last one is Alaska here. So what you see, so for example, Bethel here in Alaska, so it's clearly has very high weight in the Alaska feature, and airport like Anchorage has a large Alaska, but also a smallish large hub. Okay, so so to conclude, so we've been interested in developing some sort of novel class of statistical models, so that build on exchangeable random measure and drawing the link with the representation theorem by Kallenberg. We focus in particular to some particular example of models, so where we can have sparsity and power law properties and scalable inference. And so we've got some similar construction for directed multigraphs and bipartite graphs. So I just want to say, so since the first version of this paper, so there has been some work that builds on this approach, some theoretical work, so looking at the analysis of this of the general class of network models and the connection with the graph theory literature, so by Victor Veitch and Dan Roy, who is here, and also work by Borgs and co-authors, so at Microsoft Research. And the second line of research is so development of more structured model under this framework, so by Erlo and co-author and Constantina. Okay, so those are the two papers that are related to my talk, and so there's MATLAB code available if you want to try it. So at least for p equal 1, p greater than 1 is coming. Thank you.
Did anything depend on the link function? Any of the mathematics?
So can I change the link function?
Yeah.
Yeah. So it's everything is heavily dependent on the link function.
It's heavily.
Yeah, because it's you've got some sort of a latent Poisson construction for the model. So that yeah. So I in the sampler is heavily built on that, and the analysis I do as well. But I think Dan is
Right, the mechanics of it, but the general theory holds for.
Oh yeah. So then there's so here I'm talking about the to have inference, etc. But yeah, no, the representation theorem is just based on this notion of exchangeability.
But are there differences in the conclusions at all if you change the link function?
So what do you mean in terms of
you're using this model, right? I'm talking about the analysis of real data. If you want analysis of data which has been generated under the first model, but now analyzed under different link functions.
Yeah. So the sparsity properties are all based on this. But there are more general results. For example, by Dan and Christian on this. So it's not based on the use of a particular link function. Yeah. Was it clear? Not really.
Well, I mean, you have anything resembling, let's say, a Bernstein-von Mises theorem, anything like that?
Yeah. No. At the moment, I've got all I've got is there.
Just wondering, would you get very different behavior if you let the latent factors be negative?
The latent factor being negative.
I mean, if you allow them to be either sign.
But then you need to ensure that So you need to ensure that you get a probability here. Here I need this part to be positive.
Is the form of the link function?
So you could use something, I guess, a different link function. The issue is how do you get scalable inference from that? Yeah, because so here why do we get an algorithm that works well? Because we introduce some latent count variable. So you got some latent representation as a multigraph where you got counts on the edges, and those counts are Poisson. And so because it's all conditionally Poisson, you get this nice algorithm. So I don't know if we could get the same behavior with different link functions. Okay.
Shall we move on?
Yes.
Or maybe while Dave sets up.
Do you know how to generalize the weighted network?
Sorry?
The weighted network.
Weighted? Yeah, so in a sense the construction we have is so we first build an integer weighted network, and then we look at the projection of this integer weighted network as a undirected graph. So we've got a version for multigraphs. Yeah, I don't know if to have general weights. I don't really know.
Now starting to eat into our wine time.